This video is about how the Intermediate Value Theorem tells us about wobbly tables. I've made my wobbly table here by taking a cup and cutting it up. And you can see two of the legs are red and two of them are black, so I can keep track of them. And I've made this really uneven ground here, so you can see on the paper from the shadow maybe that this table is really wobbly, right? Okay, so I want, in order to do the math, I want you to notice something. That if I turn the table 90 degrees, I get the same situation, except that now it's the black legs that are wobbly and the red ones are sort of being the pivot element for it, right? So with that in mind, let's take a look at what the Intermediate Value Theorem says and what it says about this table situation. So I'll use an example to talk about what the Intermediate Value Theorem means for a function, and I've chosen the arctangent because it's a pretty graph. Makes this nice little S shape. And what the Intermediate Value Theorem says is if the function's known to be continuous on some interval. So I'm going to block off an interval here, and I'm only going to be concerned with that interval. The Intermediate Value Theorem says that the function can't skip points. And that's pretty obvious because it's supposed to be continuous. So this is not like some great deep thing, but what's interesting is that we can make quite a bit of this little statement. So if we know that the function starts over here and ends up here, I'm looking at the y values now. If it traverses from the y value on the left all the way to the y value on the right, that it has to go through all the y values in between. It can't have any breaks in there. That's what the Intermediate Value Theorem says. And in particular, notice for this nice little S-shaped curve that if it starts at a negative point, then ends up at a positive point, that somewhere it has to go through 0. It doesn't have to be at the origin, it could go through 0 anywhere along here. It doesn't have to be any particular shape, but if it starts somewhere negative and ends up somewhere positive, then it has to go through 0. That's one conclusion of the Intermediate Value Theorem, and that's the one we're going to use to solve the table problem. In order to talk about the table problem in math terms, we need to think of a function to deal with. So I'm going to think of r as the total distance the red table legs are from the ground. They can wobble back and forth, but there's some amount of space between those legs and the ground. And b, the same thing for the two black legs. I'm going to create a function d, which is the difference between the red ones and the black ones. So then I'm going to think of the x-axis on a graph being the amount of rotation that we put on the table. And if you think back to the video at the beginning, at first the red legs were wobbly, meaning there was some gap between them and the ground, and there was no gap at all for the black legs. That was sort of the pivot point. So originally the r minus b would have been a positive number. Then after I rotated it 90 degrees, so moving along here, after I rotated it, then the b had a positive gap between the legs and the table, and r didn't. So then r would be 0 and r minus b would be a negative number. So plotting these points on this graph means before rotation we had some point up here that's positive, that had a positive gap for the red legs, and then after we rotated it we had a gap for the black legs, and my distance function would be negative because I'm subtracting that. So if we believe that the ground is a continuous shape, and that then these distances when I do the rotation have to change in a continuous manner, the Intermediate Value Theorem says if this is a continuous curve between these 2 points, then at some point it has to go through 0. So for example, it could look like this. What does it mean if the distance function is 0? We can't have negative gaps between the table and the floor. So the only way it can be 0 is if r is 0 and b is also equal to 0. So that means there's some rotation for which the table does not wobble. So let's try it out with the video and see. Here's the original setup again. You can see we've got a gap between the ground and the red legs. And there's a total gap. If you add up the gap from the front one and the back one, even when I wobble back and forth, that total gap doesn't change. That's what I was calling r. After I rotate it, that same gap exists, except now it's on left on the black legs. That was what I called B. And the red legs now have no gap whatsoever. Notice that I can't simultaneously have red gaps and black gaps unless the table's got, balancing on two legs or something like that. We'll rule that out. So according to the intermediate value theorem, there ought to be some point at which that function equals 0 when we subtract the red and the black gap. And we should be able to get that by rotating. So if I rotate, just keep turning the table, you'll see at some point right about there, all four legs are on the ground. And that has to happen as long as the ground is continuous, according to the intermediate value theorem. Okay, so one last thing. What I've done here is I gimped the table up by damaging one of the legs, so it really, really wobbles now. And the other legs are all the same, but this one's much shorter, so you can see the gap between the ground and the black legs is pretty large. And if I rotate it on my smooth, continuous surface here, it doesn't seem to help. It's still wobbly. So why is that? How did the intermediate value theorem fail us here? Stop the video for a second, think about it, and see if you can figure out what the deal is. Well, remember, the intermediate value theorem just says we can't skip values if the function's continuous. So we were guaranteed there would be a non-wobble zone because we started with a gap on one set of legs, and then we could turn the table so that the gap was on the other set of the legs. And we created a function so that this created a positive number here and a negative number there. The graph now doesn't have that property, because the gap is on very large on the black legs. I've got a dot down here, 0 minus some large number. Before, it was obvious that if we turned the table 90 degrees, we would reverse the situation. But here, we don't have that property because the table's not symmetrical anymore. So no matter how I rotate it, I continue to have this gap in the bottom. So the reason the intermediate value theorem doesn't really help us here is because we lost the property of symmetry with the table, which made it obvious that if I rotated it 90 degrees, it would make a graph that goes from positive to negative or negative to positive. So in our case, there's no guarantee that it's going to cross 0, and that's why there's no balance point. And this kind of looks like a hot dog, so I'm going to add some ketchup and some mustard and maybe some pickles. Okay, some pickles. Oh wait, I gotta film it. What kind of pickles are that? There we go. There's the pickles. Okay. Alright, that's it.